Classical quantum mechanics relies on a highly intuitive baseline. To trap a particle, you need a trap. According to the foundational Sturm-Liouville theory, quantum bound states inherently require a confining potential well to exist. The inverse of this rule is just as straightforward. Continuous spectra represent delocalized states. If you place a wave on an expulsive potential, a mathematical hill rather than a bowl, it will simply scatter infinitely outward. These wave dynamics are governed by the Schrödinger equation, the primary mathematical framework for modeling how quantum states evolve over time and space. For decades, physicists treated the rule of confinement as an absolute. The first verified exception arrived in 1929, when John von Neumann and Eugene Wigner documented a phenomenon now known as bound states in the continuum. Wigner mathematically proved that a localized, normalizable wave function could exist within a specific three-dimensional isotropic expulsive potential. He demonstrated a wave trapped on a hill. This discovery carried severe constraints. The von Neumann-Wigner state only functions under highly specific mathematical parameters, and it yields exactly one discrete zero-energy eigenvalue. Because of its rarity and strict limitations, this state cemented a widespread assumption. Physicists concluded that expulsive potentials are broadly useless for trapping waves across a continuous energy spectrum. Recent research reevaluates that assumption. By solving one- and two-dimensional Schrödinger equations, physicists have shown that expulsive potentials do not inherently lead to widespread delocalization. This graph maps the geometric condition for the anomaly. The standard quadratic inverted curve, an antiharmonic oscillator where the steepness factor gamma equals 1, is overlaid with a steeper quartic curve, where gamma equals 2. The potential must be strictly steeper than the standard quadratic curve. Crossing this steepness threshold forces the wave to undergo rapid, extreme phase oscillations. These dense oscillations create an effective self-trapping mechanism entirely within the linear system. Unlike the von Neumann-Wigner state, which requires a single zero energy level, this linear self-trapping occurs across a full continuous spectrum, applying to all real eigenvalues from negative to positive infinity. By proving that steep inverted hills trap wave functions at all energy levels, this finding mathematically expands the known boundary of BICs. It provides the specific criteria necessary to design optical traps without relying on physical boundaries. To trace exactly how a wave traps itself on a steep hill, we look at the one-dimensional stationary Schrödinger equation utilizing an expulsive potential. We establish the baseline edge case, an antiharmonic oscillator where the steepness variable, gamma, is exactly equal to 1. This graph charts the wave function's asymptotic expansion moving outward. At gamma equals 1, the equation develops a specific logarithmic correction to its phase, the natural log of absolute x. The consequence is divergence. The integral norm slowly but infinitely diverges over distance. Because this norm diverges, the wave cannot be considered truly normalizable or bound. The standard quadratic hill behaves exactly as classical physics predicts. The particle escapes. We now cross the steepness threshold, increasing the expulsive potential from quadratic to quartic, setting gamma equal to 2. In classical physics, a single particle rolling down this new ultra-steep mathematical slope undergoes exponential nearly infinite acceleration. This plot translates classical acceleration into quantum mechanics. Extreme acceleration forces the wave function's phase to oscillate violently moving outward, compressing peak frequency.
The asymptotic expansion's third-order correction determines this frequency, mathematically linking the steepness gradient directly to the density of phase oscillations. These dense oscillations force the integral norm to mathematically converge. The wave effectively self-traps. Effective self-trapping does not strictly require nonlinear interactions. Extreme acceleration from steep linear gradients provides its own mathematical cage, altering the standard rules for wave localization. Because the integral norm converges for any gamma strictly greater than 1, this trapping applies to all eigenvalues from negative infinity to positive infinity. We can test the limits of this behavior by subjecting the eigenstates to massive, absolute negative eigenvalues. This plot demonstrates the effect of massive negative energy. The core area is severely suppressed, forcing the wave outward into a flattened core before peaking. Transitioning to a log-log scale reveals that as absolute energy scales up,
the peak amplitude's coordinate pushes outward logarithmically. Mapping this extreme core suppression gives physicists a predictable model. They can precisely calculate and control where wave energy peaks within a completely unconfined system. These one-dimensional self-trapping mechanics map directly into the two-dimensional paraxial propagation models utilized in modern photonics. In this 2D plane, we introduce integer vorticity, S, representing angular momentum. The research identifies a precise mathematical condition where the exact analytical vortex solution emerges. The potential steepness must be perfectly synchronized with the state's angular momentum, following the relation gamma equals 2s minus 1. This 3D topological map shows the structural outcome of that equation. When the steep expulsive gradient profile synchronizes with the rotational momentum vector, it locks into a stable, perfectly formed topological vortex ring. This edge case bridges pure mathematics to optical engineering. It dictates the exact topological specifications needed to program optical potentials, trapping spinning light beams in open space. For practical implementation in ultracold atomic gases, the linear Schrödinger equation connects to the Gross-Pediavsky equation. In applied Bose-Einstein condensates, interatomic collisions generate a cubic self-focusing nonlinearity. This inherent attraction deforms the linear eigenstates. These collisions introduce an attractive, self-focusing force. If the state's norm, effectively the number of atoms present, exceeds a critical threshold, this attraction overwhelms the linear trap. Even a tiny spatial perturbation can pull the peak off-center, triggering what physicists call a parity-breaking instability. Engineers can avoid this instability by projecting a blue-detuned laser modeled to the mathematically verified steepness profile. They can safely trap Bose-Einstein condensates, or paraxial light, just beneath the critical norm. Because bound states in the continuum can be successfully engineered using steep expulsive gradients, physicists have the specific mathematical parameters required to generate spatial solitons and optical traps, entirely free of physical boundaries. We started with the strict confinement parameters of Sturm-Liouville theory, arriving at the mathematical proof that extreme linear acceleration can effectively trap wave states across an open, continuous spectrum. If you enjoyed this video, please give a like and subscribe, and what would be really helpful would be some suggestions for future videos. Today's video was brought to you by Synestic Systems LLC, founded by Shane Persinger.